People who work at a job earn money for the work they do each day. You get paid by the hour, then for every hour worked, you'll earn a specific amount. For instance, suppose your job pays $8 per hour and you work 5 hours in a day. How much money would you earn over that 5-hour period? We can create an arithmetic sequence to figure it out. An arithmetic sequence is a sequence that increases or decreases by the same number, with each position in the sequence like this: 8, 16, 24, 32, 40. The amount here increases by 8 each time. When you earn money, it's useful to save some of it in a bank account that earns interest. Over time, and if you keep saving, your money will earn interest on the interest, so you earn more money faster. That's called compound interest. When you have it, the growing total forms a geometric sequence of numbers. A geometric sequence increases or decreases by a constant ratio of one term to the previous term. For example, if the ratio is 2, you simply double the previous value in the sequence. 1, 2, 4, 8, 16, 32, 64, 128, and on and on. But arithmetic and geometric sequences don't have to increase. They can decrease too. For example, amounts of radioactive elements, like uranium-238, decrease in nature. These elements decay at a fixed rate, called their half-life. It's how long it takes for half, or 50%, of the amount to change to another element over time. Let's look at examples of arithmetic and geometric sequences in more detail. Money. It's what you earn when you work. In many cases, the amount of money you make depends on the number of hours you work. Suppose you land a job that pays $8 per hour. That's $8 for every hour you work. If you work 5 hours each day, the total amount of money you earn hour by hour can be expressed in an arithmetic sequence like this. Each hour you earn $8 more, so each total is a multiple of 8. There's a constant difference between the terms. Here, it's 8. This makes it an arithmetic sequence. You've been earning a total of $40 each day, $8 per hour for 5 hours. Now, if you do that 4 days a week, how much total money would you have earned for the week so far by the end of each day? We can build a number sequence to find that out. At $40 each day for 4 days, the sequence would look like this: 40, 80, 120, 160. Every day, you'd have $40 more than you did the day before. Did you notice that each number in the sequence increases by 40? That's because each number in the sequence is a multiple of 40. Arithmetic number sequences can decrease as well by the same number each time, even rolling into negative figures. Let's reverse our earlier sequence from 8, 16, 24, 32, 40 to 40, 32, 24, 16, 8, 0. If we keep going, the sequence would look like this: -8, -16, -24, -32, -40. There's still a constant difference between the terms, so it's still an arithmetic sequence. But now, instead of 8, it's -8 from one to the next. Thousands of years ago, there weren't as many people around, only about 300 million of us, or 0.3 billion, roaming the Earth in year 1. But with each passing year, the world got a little more crowded. By 1750, the human population had climbed to about 790 million. By 1800, there were almost 1 billion people on Earth. If we show this population growth on a graph, it looks explosive. See how quickly the line graph climbs? That's because population increases geometrically. When it's not very crowded, it takes longer for the increase to be noticed. A geometric sequence increases or decreases by a constant ratio of one term to the previous term. For instance, in the year 2000, the average yearly growth rate for human population was about 1.4%. That means the population increased by 1.4% per year, or 0.014 times the amount it had the year before. If we start with the roughly 6 billion people in the world, the next year there would be about 85 million more people worldwide. At the same growth rate, the following year, the population would add almost 87 million more people, and then 88 million, then 89 million, then more than 90 million. The numbers keep getting bigger and bigger, more and more quickly, because they're increasing at the same percentage of a growing number. Each year, with geometric growth continuing at this rate, the number of people living on our planet would be 1.014 times the amount from the previous year. At this rate, every 50 years, the population would double. Our population could continue at that geometric increase if there were enough room and resources. But at some point, our resources, like water, food, even space to live and play, won't be enough. So this increase can't continue in the same pattern forever. Many factors influence growth rate worldwide, including education. Australia, home of cute koalas and leaping kangaroos. But there's much more to the land down under. The Northern Territories are home to one of the oldest cultures on Earth, the Aborigines. Since they arrived long before written language, no one was sure when they arrived. To figure out dates of ancient events, scientists use a technique called carbon-14 dating. Carbon is an element present in every living thing. The amount of carbon-14 compared to the total amount of carbon is about the same in all living things. But when an organism dies, the carbon-14 decays at a fixed rate, called its half-life. Every 5,730 years, the given amount of carbon-14 in the object, compared to the total carbon, decreases by half or 50%. To figure out how old these aboriginal rock paintings are, experts take a tiny fleck of the paint that was used. The paint comes from plants and organisms that lived at that time. Then, they compare the amount of carbon-14 remaining to the total amount of carbon, using a table like this. The information forms a geometric sequence because it always decreases by a set multiple or ratio. In carbon-14 dating, every 5,730 years, there is 1/2, or 50%, of the amount at the beginning of the given time. As you can see by the graph, the numbers in the sequence get smaller very quickly. But they never get to zero, just smaller and smaller until amounts that remain are too small to measure. The decreasing geometric sequence allows scientists to date artifacts and fossils from around the world up to 50,000 years ago. Experts measure other substances in the same way to date even older artifacts.